Welcome to RLD Academy. In this video, we are going to discuss very basic concepts of voltage amplifiers. In particular, we will be discussing following points. What is voltage amplifier and its applications in different areas. We will be discussing about the simplified model of the voltage amplifier. And this concept is very much useful because if you understand the basic concept of this simplified model, then you can use the voltage amplifier in different areas, like when you will be handling one active filters where amplifier is with some other filtering circuits like capacitor, inductor. There you can handle it easily. Or suppose if voltage amplifier is used with some negative feedback, then also you can handle it properly. So very simplified model of voltage amplifier, this knowledge is required, and we will be discussing this concept in detail here. We will also discuss the loading effect on the voltage amplifiers. One voltage amplifier in isolated form, when there is no source is connected, no load is connected, then it can give you some good amplification factors, means voltage gain. But whenever a source is connected, a practical source is connected, or a practical load is connected, that time you may not get that much high gain. So gain is reduced. That is called loading effect. That will be discussed in detail. And how to find the overall voltage gain with those practical voltage source and practical load with this amplifier, that will be discussed in detail. So this video is going to be very much useful. Follow this video thoroughly. Don't skip any part. I hope it will be useful for you. Now this is one voltage amplifier. As it is a system, obviously it will accept one input and will produce corresponding output. So we can consider the input is VIT and output voltage is V0T. This output voltage for this voltage amplifier could be proportional to this input voltage Vi. So this ratio of V0 upon Vi is constant AV, that is called voltage gain. So generally this voltage gain should be more than 1, then only it will be called voltage amplifier. If it is less than 1, then it will be considered as attenuated. Right. Now what type of voltage it can accept this Vi? So generally we are using this VIT as sinusoidal signals. Suppose if it is A sine of omega naught t, A is the amplitude, omega naught is the frequency. So this is the height A and this is the minus A. So signal is bounded between plus A and minus A. It will oscillate in this way. Now if it is applied to this voltage amplifier, we can expect that its amplitude is amplified. It's not that frequency is amplifying or something else. So only the amplitude will be modified, but frequency will remain same. So we can have this kind of shape. Okay, you can see this height is amplified. It is AV times A or minus AV times A, this negative side. But frequency will remain same. Suppose this original signal is having frequency 1 kilohertz. So this signal should have also 1 kilohertz. Okay, means 1 second, if there are 1000 cycles in the input signal, in the output signal also in 1 second there should be 1000 cycles. So this is the meaning that frequency will remain same, only amplitude is modified, it is increased. That is the voltage amplifier. And remember that this sinusoidal signal is used generally for testing purpose. But remember, this is not only the signal that could be applied to the voltage amplifier. We can apply any other signal, like any time varying signal which will carry some information that could be applied to the voltage amplifier, and we will get some amplified version of this signal. So we can expect this kind of output from this voltage amplifier. But remember, DC cannot be used at the input of the voltage amplifier. We are not considering that voltage amplifier will amplify the DC signal. So generally we will apply the AC signal or time varying signal at the input side, and we are expecting some high amplitude the signals at the output side. Now I'll show you one practical example. So this is one microphone, a practical one. So if you speak in front of a microphone, then this microphone will produce some electrical signal at this end, and we can use one speaker to get more sound. Suppose there is one stage performance, one singer is performing on a stage, and there is a live show. So that song should be amplified directly through a speaker. So we need to connect the output of this microphone to the speaker, okay? But before that, we need one amplifier to amplify this signal, because the output of this microphone, this voltage level is very low. So first we need to amplify it. For that I need one amplifier. Then output of this amplifier can be fed to the speaker to get louder sound. So this could be the connection. So this output is connected to the input of the voltage amplifier, and output of this voltage amplifier is connected to the speaker. Then we can expect a louder sound from the speaker. So this is one practical example. Now we'll discuss limitation of voltage amplifier. So first one is linear range in amplitude. So what is the meaning of linear range? So do you think that this relation V0 equals to AV times VIT is always true for any voltage level VIT? For practical voltage amplifier, it is not always true. So what we can find that for certain range of input signal, the output is linear. So this slope is high, this slope is AV actually. This AV is the slope, this V0 upon Vi is constant, this slope, it is both side I can consider, negative side and positive side, but beyond certain level, its output will saturate. Okay, so means V0 is becoming constant though input voltage is more. So this is a limitation of practical voltage amplifier. So practical voltage amplifier can have a linear range, a small linear range. Within that only signal should lie, then only you will get the complete amplification factor. Okay. So if I apply, this is your VIT, I can get the corresponding amplified version. But if it is beyond, so this input voltage is too large or too strong, then some part of this signal could be clipped off. Okay, like this one. So it is amplifying this one. So its maximum voltage level is this one. This is the maximum output voltage level. So beyond that, this part is truncated. It is clipped off. So I can get some distortion at this end because of this limitation of linear range. So amplitude of this input signal should be sufficiently low. It should lie within the linear range. Then only you can get faithful amplification. Otherwise, you are going to get some truncation, some distortion. So this is the first limitation. Second one is finite bandwidth. That is with respect to frequency range. So do you think that any signal Vi could be applied and we can get amplified version at the output end? Any frequency of signal, 1 kHz, 1 MHz, 1 GHz, anything could be applied? It is not true always. Okay, one practical voltage amplifier will have certain limitation. A band of frequency only it can amplify properly. So if it is out of that band, then its amplification factor will reduce. Like this. So if this is the linear range, this is a flat gain we can get. So this flat gain is true for certain band, certain frequencies. This frequency range, the gain is flat. It's not changing. Everywhere you will get the same gain. Suppose AV equals to 10, so means every frequency at 1 kHz, 10 kHz, suppose it is 20 kHz, everywhere you will get the gain of 20 only. Okay, but for very low frequency, the gain is falling. Again, for very high frequency, gain is also falling. So in mid frequency, you will get a flat gain. Okay, so there only we'll try to use the amplifier in this range. Okay, all the signals will be amplified in same proportionate, right? Will give you the constant gain. otherwise gain is reduced this side. So there is certain reason for this bending and this bending. So this low frequency bending is basically due to external capacity effect. If you use some capacitor in the circuit with this voltage amplifier, that time you will get this kind of bending here. And this high frequency bending is generally for the capacitance inside the amplifier, means BJT or MOSFET. The parasitic capacitance are responsible for this bending. Those will be discussed in detail in other videos. Now, how to design the voltage amplifiers? We can design voltage amplifier using transistors like BJT, bipolar junction transistors, or MOSFET, metal oxide semiconductor field effect transistors. So this is one circuit, a complete circuit for a voltage amplifier. Don't be scared about this circuit. So it's not that much difficult to understand about the circuit, but this class is not for that. So here you will find lots of resistances along with the transistors, capacitor and VI, the input source, all those things. Now we need to discuss here that which one is the main element. So main element is this one, this BJT, bipolar junction transistors, right? So from this we can get one amplification factor, but it cannot work alone. So we need to add more circuitry so that it can work properly. Okay, so first we should add some resistances, and we should fix up one Q point or quiescent point so that both the side, negative side and positive side, input signal is changing. That time we will get faithful amplification in the output side. So those will be discussed in detail, but remember here that this is the input signal VI, this is the AC signal, but this VCC is a DC voltage source applied, but this is not for the input signal, right? This is for just to bias this transistor in the active range so that it can amplify. Not only this R1, R2, RC, RE, these four resistors are used to make the system robust, means so that it can work properly, it can amplify the signal. Okay, it should be in active region. You know that transistors, so that thing I have discussed in my previous videos, that we can have four different regions. One is cutoff region, saturation region, forward active, inverse active. Okay, in forward active region, this amplifier is used as an amplifier. So we have to make sure that transistors will be in active region, forward active region. For that purpose, we will add these elements R1, R2, RC and RE. This is the purpose. And then to connect this input voltage to this amplifier, we will use this capacitor, that is called coupling capacitor, and another capacitor C2 when we will use some load here with this amplifier. So these are two coupling capacitors. So because of these two, we can get some bending in the low frequencies that I have discussed. So along with this one, there is one more capacitor externally connected across RE. This is called bypass capacitor, right? So this circuit will be discussed in detail, but here we will be discussing the model for this BJT in detail. This is the main aim of this video. So if you are enjoying this video so far, you may just press the like button. We'll continue. Now this is your voltage amplifier. Now I'll consider two-port model. It will be better for us to understand. So this is the input side, VI potential. This is the output side, V0. Now the gain of this voltage amplifier is suppose AV. AV is the voltage gain. Now this is not the sufficient parameter to characterize this voltage amplifier. Along with this voltage gain, we also need to consider this input resistance. The resistance, if you look from input side, so this amplifier will offer certain resistance. That resistance is called input resistance. Similarly, from output side, if you look at, again you will find some resistance or not. That is your output resistance. So input resistance Ri, output distance R naught, and the voltage gain AV. These three parameters, at least it should be there with the voltage amplifiers. Now how to get the model with these three parameters? So for that model, we'll consider one baseline. This is the baseline, and this is your input signal VIT, that is your output signal V0 T. Now we'll connect input resistance this side, input side, because device will offer one input resistance, that is your RI. So this circuit I will close. So this input side is independent from right side. Okay, that model we will consider. And then as this amplifier will offer one gain AV, voltage gain AV, so whatever voltage will appear across this input RI, so here we are going to get AV times of VI. So I need to consider one dependent voltage source which is depending on the voltage level across the RI. So voltage dependent voltage source, that we will consider here. So this symbol we will use for dependent source. Now consider about this R0, the output resistance. Whenever we will consider one practical source, voltage source, the resistance, source resistance should be connected in series with the voltage. So as it is a voltage source, this resistance R0 should be connected in series. So here it should be connected like this. So this is your series simplified model. Input resistance Ri connected to input side, and depending on the voltage level Vi which will appear across Ri, we will get one dependent source AV times Vi, and we will have one source resistance R0, basically it is output resistance. Okay, then this side we will call it V0. Remember, this simplified model is for that mid band when there is no frequency effect, the gain is flat. That time this model will be used. But low frequency and high frequency, some capacitive effect will be there, those will be discussed later. For low frequencies, I said that those external capacitors, that for coupling one, that C1, C2 or CE, those will be connected this side or this side. Okay, that's how we will get some bending, but model will remain same. This model will remain same. So this model is good for low band, low frequency as well as mid frequency, but this is not complete for high frequency model, because if I consider very high frequency, then some parasitic capacitance will come into picture that we need to include. So that time we will consider pi model to replace this voltage amplifier. So we will have some capacitor here, the across Ri, and also we can have one capacitor here. Those will be discussed in detail later. Those are the pi model we will be discussing. Okay, there we will find some capacitance in the model. Because of that, you will get some bending for high frequencies. Okay, so this is your very simplified model. Okay, so I hope you have understood this model. Now I will connect one source. So this voltage source Vs with source resistance Rs. Rs is source resistance. Similarly, we will connect one load, practical load RL. Now you can notice that I have given you one practical example, that one microphone is connected input side to the amplifier, and one speaker is connected at the output side of the amplifier. Okay, so this speaker is the load. So speaker resistance will be the RL here in this case. This is the RL is the load resistance, means speaker's resistance, and here this RS is the resistance of that microphone, source resistance. It is the resistance of the microphone. Okay. Now whenever the source resistance and load resistance are connected, then we are interested to find out overall gain. So what is actually, so now here I will consider this voltage level across this RL is VL. Okay, this VL upon VS, this actual source voltage, this ratio is overall voltage gain. So that we want to find out. You can notice that this VI and open load condition, if RL is not connected, then VL will be same as AV VI. Then this ratio AV VI upon VI will cancel, you will get only AV. But whenever load is connected or source is connected, you may not get same gain AV. Okay, that we want to discuss right now. So VI, how to find this VI? Now look at this input side carefully. So this is your source. With the source, this is source resistance. This is your resistance Ri connected. All are in series. So this is one series circuit and it is completely independent from this side. So we can analyze this one. So as two resistors are connected in series with one source, I can use potential divider circuit that I have discussed in my previous videos. You can go through. So voltage across this Ri will be the same resistance Ri upon total resistance Rs plus Ri times Vs, the supply voltage. So this is your Vi, right? Now I will consider the output side. In this output side, the VL. How to find the VL? Now again you will see this circuit. Now this is complete circuit. Now this voltage is AV times Vi and this is R0, this is RL. Yeah, but this voltage level, it is depending on this Vi. That's fine, but once this Vi is known, that this voltage is also constant, and then we can find the voltage across this resistance RL. Again we can use potential divider circuit. So potential across RL will be the same resistance RL upon total resistance R0 plus RL times the supply voltage. Here it is AV times Vi, right? So we have got these two equations. Now here this VIT I can replace from here. This is your VIT, so that I can replace here. So what I will get? RL upon R0 plus RL times AV, and this is your VIT is Ri upon Rs plus Ri, it should be Ri times VST, right? Now from here we can get this ratio VLT upon VST. So these parameters, okay? So this factor is, first factor is RL upon R0 plus RL, second factor is Ri upon Rs plus Ri multiplied with AV. So you see earlier gain was only AV, now overall gain is this much. So this is your overall gain, I'll call it AV prime. Okay, now you can notice on this factor RL upon R0 plus RL. So all the resistance are positive. R0, RL, Ri, Rs, all are positive. So this numerator is less than the denominator. So obviously this fraction is less than 1. Similarly this fraction Ri upon Ri plus Rs, this is more than this one. So this is also less than 1. So as this is less than 1, this is less than 1. Obviously they are multiplied. So AV prime should be less than AV. This is actually loading effect. Whenever you will connect practical source, practical load, then you are going to get low gain, some reduced gain, and reduced by these factors. These are the two factors. Okay. So if you understand this thing, in 1 second we can find out overall gain. Just see a very simple one. What is the factor? The input side, this factor, this Ri upon Rs plus Ri. In output side, what is the factor? This RL upon R0 plus RL. That's all. These two will multiply. So for better voltage amplifier, we want to get more gain even though the source is connected and load is connected. So we can get maximum, it is 1, close to 1, and it is also close to 1. So when we will get close to 1, what is the condition on R0? What is the condition on Ri? That we want to find out. So you can see that if Ri is very large compared to Rs, then this ratio is close to 1. So Ri is very large compared to Rs. Similarly here, if R0 is very small compared to RL, then this two will be again close to 1. Okay. So Ri should be, this Ri should be very large compared to Rs, then only maximum voltage will appear across this Ri. That voltage will be amplified further. Okay. Similarly, this voltage will be available at the output end if R0 is low, because if R0 is large, more drop will be across R0. Then we will get less voltage across the load. So to get maximum voltage across the load, this R0 should be very small compared to RL. So this is the logic. This Ri should be very large compared to Rs because I want more voltage across this end, input side of the amplifier, and This R naught should be very low because there should be little drop across the R naught so that maximum voltage will be available at the load. Okay. So for the ideal voltage amplifier, the Ri should be close to infinity and R naught is as low as possible, close to 0. So this is a true limiting case. Ri is close to infinity for ideally and R naught is close to 0, short circuit. This is open circuit and this is short circuit. So this same voltage Vi will be coming and there is no drop, same AV Vi will be available here. So voltage gain will remain AV, no reduction if it is ideal voltage amplifier. Any voltage source you will connect, any load you will connect, you are going to get same gain AV. Now if I will give you one example. Suppose Rs equal to Ri equal to 1 kilo ohm and RL equal to R naught equals to 100 ohm and AV suppose 100. Can you find overall gain? That is very easy. So AV prime will be this factor, this Ri upon Rs plus Ri times this side RL upon R naught plus RL times AV. So as it is given both are same, so this is 1, this is 1 plus 1 2, so half. Similarly here 100 upon 100 plus 100, 100 by 200, again it is half. So this is half and this one is 100. So this is half and 100, 100 by 4 is 25. You can notice that the amplifier can amplify up to 100 gain factors, can produce 100 gain factors, but with this source and load we may get only gain of 25. So 1/4 only of the gain, maximum gain is available right now. So this is because of this loading effect. Okay, I hope you have enjoyed the video, and if you have enjoyed these things, please press the like button, and if you have not subscribed the channel, if you want to get this kind of videos in futures, then you may subscribe the channel. I'll be adding lots of videos. So thanks for watching.